Right, guys, hello. This is a presentation titled The Security Wolf of Wall Street, Fighting Crime with High-Frequency Classification and Natural Language Processing. So we're super excited to be here today. Thank you so much for inviting us, Data by the Bay. This is really great. So actually one of the first times we're actually speaking in San Francisco. We speak like in a lot of different conferences, but not so much in San Francisco. So first, let me just introduce myself real quick. My name is Thibault, and I am the Manager of Development and Research at OpenDNS. You may or may not know me with another project that I've worked on. It's called Open Graffiti, which is a data visualization platform using OpenGL and 3D graphics. But more recently, I've developed the Avalanche project, which we're going to talk about in this presentation. And the main focus of my research, obviously data visualization, 3D graphics, graph theory, but especially real-time systems.
Cool, and thank you for having us, and thank you for attending. My name is Jeremiah. I'm really excited to be here. Friends with Alexi. Met a while ago at a text processing meetup. So yeah, I'm a scientist at OpenDNS, now Cisco, and basically went to school in San Francisco, got my master's in computer science. As mentioned before, worked for Evernote and Uber, also Mandiant, which is now FireEye, if you guys know about that. And I just like to solve interesting problems, and proud SPCA puppy owner, and we got a really nice presentation for you guys. So really cool stuff. So you guys will be excited.
Thank you, Jeremiah. So the agenda for today, so introduction, and then we're going to talk a little bit about the Avalanche project and the research pipeline. So essentially, I'm going to describe the whole kind of data processing pipeline that we have, and a couple of data mining techniques that we're using, in real time on our cluster. And then we're going to talk about NLP rank, which is one of those classifiers who's running on this data processing pipeline, which is doing phishing detection. Okay, cool. So let's get started.
So yeah, just a little bit about OpenDNS Labs. I like to think where it's kind of data science meets network security. And data science is kind of new to the security field, so it's kind of still being developed, but we feel we're at the forefront. And basically every day we deal with over 100 billion DNS requests per day. And a little bit more about us, we're now have a proxy, so we process about 10.1 million requests of HTTP traffic, and now including HTTPS too. So yeah, on a daily basis, we write detection algorithms, do security data analysis, distributed systems, and big data engineering, and this guy's the king of data viz, so yeah.
Thanks. Cool. So with that much traffic, one of the main challenges that we have is really to go real time on this. So first, allow me to say something. I do know what real time means, and in this case, I'm just going to use like a kind of a soft definition of real time. What I actually mean every time I'm going to use the word real time is near real time. So essentially, yeah, if you're familiar with real time systems, so please forgive me for that. It's just easier to say. So the Avalanche project, I would like to start this presentation with a quick analogy, because really it's very close to what we do. This is the title also of the presentation. Really the analogy with what they do in stock market and like the algorithmic trading. First you have a stock exchange, you have usually a quant server, and then they run a couple of strategies, and that loops back through an execution kind of an engine to execute the trades. And then they obviously measure how the strategies are doing, portfolio, risk management, stuff like that. But they also store historical logs, like the historical data of the stock market to be able to run their models and to do back testing on those models. And really, when you think about it, it's not that far from what we're doing. Really, for us, we see like a huge amount of traffic coming from resolvers, again, like 100 billion queries per day. And really, we store those logs, we aggregate those logs in S3 or like Hadoop, a lot of different ways. And we run those models, we do some back testing, which is our machine learning kind of training process. And really the execution that we have is to have an impact directly on the resolver, so doing some blocking, whitelisting, or domain tagging, or any sort of thing that is going to affect the traffic in some way. And obviously to do that, we run a couple of models, a couple of classifiers. And for us, really the analogy with the portfolio and risk management is to have some sort of predicted impact on our users. Obviously, if for some reason one of the classifiers were to block google.com, you would think about it twice. We have all sorts of techniques to avoid that, obviously. But yeah, so just really, I think it's interesting to understand that we have to deal with super, super fast and heavy data. And we have challenges that are very close to what they do on the stock market. So this is exactly the reason why I started developing this project called Avalanche. and it's an open source project. So a lot of the plugins that we've developed for that project are actually intellectual property that we have to keep, but the core engine is actually open source, and you guys can actually check it out if you're interested. So it's a real-time data processing framework. It's completely modular, parallel, and distributed design, and it's written using Python and ZeroMQ. And ZeroMQ is widely known in the finance world if you're familiar with it. It's a great, great library. Seriously, like, kudos to these guys. They've done an amazing, amazing job. And really for us, it's the platform, a lot of real-time OpenDNS models. These ones are private, as I said, so NLP rank, which we're going to discuss today. But also we do some sort of DNS tunneling detection, a lot of DGA detection as well, and fast flux. These are all challenges that we have in the security world, and you may or may not be familiar with those, but I invite you to check them out. So really the whole paradigm of the Avalanche project is to be able to design data processing pipelines this way. So it's like a graph, like a data processing graph. So all these nodes that you see here are plugins, threads, and then you can also assemble nodes together, so threads together, to merge them into only one thread, and that's what I call a rack. So really the idea is to develop this whole processing pipeline that's going to come from one or several origins, and be able to process this data as fast as possible using ZeroMQ and Python plugins. And then when I zoom in on this pipeline, the node level, this is what happens. So basically a node is a plugin, some code. I'm going to show you some code after that. And it has an input queue and output queue, which are both managed by ZeroMQ sockets. So really ZeroMQ sockets can be seen as standard sockets, smart sockets. That's the way I like to put it. There's a lot of strategies, the way you can actually manage those sockets, how they handle disconnections, how they queue up messages. I really invite you to read the documentation. It's really amazing work. So all those nodes are connected together, and this is how the code looks like. Here you have two examples of plugins if you were to use the Avalanche engine. So the first one is like a simple version. You just have one method, process message, and it returns the message, which means that the message is sent to the rest of the pipeline, so the following nodes. And then the other one is one that can run like kind of in standalone mode. So it runs in its own thread, so in an infinite loop. So here it reads data from the input, like can I do some processing here, like I'm actually loading it in a JSON message, and then you can actually send it to the next nodes as well. So these are very, very, very basic templates that you can use to actually start playing with it. Okay, cool. So that was the Avalanche project. Now, how do we use that, inside OpenDNS? And really, this is the interesting part, because this is the tool that we actually wrote to be able to process all this data that we see. So first, I'm going to do like a high-level view, and I'm going to zoom in progressively. So at first, we have our DNS resolvers right here. And it turns out that we actually store some of the logs in S3. So the resolvers basically send log chunks every 10 minutes or something like that, and we have 10 minutes log chunks that we have to process coming from all the different regions in the world. We have really a worldwide presence, so we have resolvers everywhere. And then we run this data, we replay those log chunks through Avalanche, and then it gets sent to production, so meaning blocking, whitelisting, domain tagging, all these things. Okay, now let's zoom in on the Avalanche cluster, so only on this Avalanche node there. So it's actually composed, it's a really simple grid kind of architecture with a master-slave strategy. And right now I have 8 Amazon instances. These are C4 2x large for people who are interested in AWS configuration. And really the master is acting as a load balancer, so essentially it knows which slave is busy or not, and just organizes the work and which slave can actually replay which log chunk. And one really key important part of design is that it's actually a fire and forget strategy, which means that if for some reason the master queues up the log chunks, so we have too much work we can handle, we basically start dropping older chunks. So for us, it's more important to process fresh stuff, fresh content, to discover new stuff we don't know about, to stay as real time as possible, rather than make sure we can process everything, because we have so much traffic anyway. So really for us, it's important to find fresh and like really accurate stuff. And then after that, after this processing, obviously we centralize all the results, and this is how they get sent after that to production. Now if I zoom in to the actual slave level, What we have is basically 4 processes per instance. And these are basically avalanche pipelines, so the first avalanche graphs that I've shown you before. And they keep processing this data in parallel. And again, this pipeline is also composed of a lot of different threads. And total right now we have 8 instances, 4, so 8 times 2, 32, and composed of a pipeline of a lot of different threads, which are described here. So this is a simplified version of this data processing pipeline. So at first we have obviously the master who sends the work, and then the streamer who replays all those logs. And then the first thing we do, all our ucache, just to decrease the amount of traffic that we see. The DNS traffic is extremely redundant, so we really, really want to decrease the amount of traffic we have to process. Unless you're doing some time series calculations or you need the actual timestamps of the DNS request, there's really no need to reprocess the same thing. And then it goes through a domain tagger. So this is where we do the pre-filtering. So whitelisting, blacklisting, things we already know, basically. We take out things we already know. We have a couple of, we have a matcher that basically takes out a couple of IPs, sinkhole IPs especially. And then we enrich this information by the GeoIP, the MaxMind plugin. So this helps us to get the ASN information from the IP in our logs. And then this thing is split into a couple of classifiers. Again, this is not, there's also the fast flux that is missing here. But today we're going to talk about the NLP rank 1 here. And then once this process is done, we have to go through what we call a miner stage, right? And this miner is really, I'm going to describe it later in the presentation, but the idea is to use other indicators, external indicators coming from other APIs, even ours, to be able to do kind of graph detection techniques, apply graph detection techniques on it. Then we have some filtering phase just to make sure we take off like a couple of details or false positives, and then it goes directly to production. Cool. Now, a couple of numbers, because I think it's really evocative. It's really nice to see those numbers. These are numbers I've extracted from our logs, and this shows you the message rate that we're actually seeing at the resolver level. And I chose the Amsterdam resolver, which is kind of not the biggest, not the lowest, kind of average resolver. The biggest we have is Miami. Lowest, I'm not sure, Singapore probably. And I took a log chunk at noon UTC, which is noon in Amsterdam, around noon, which is peak time usually in our logs. So query logs are, so if you're not familiar with the DNS traffic, really the way you can think about it is question and answer. Query log is between you and the resolver, and auth logs are between the resolver and the authoritative network that is behind. And really what you're seeing here is the number of user requests. So here we have 10,000 requests per second at noon, and at midnight like something like half of that. And I run a couple of benchmarks with Avalanche, so really we can process 30,000 messages per second, which is one message every 33 microseconds. So really you see the parallel with the kind of what they do in the stock market when you have to deal with data so fast. So honestly, it's I can't really take credit for that. ZeroMQ is doing all the job. All the work is really this socket and message processing engine that they have is completely amazing. So really we can run our logs, replay our logs 3 times as faster than Amsterdam. Again, Amsterdam is not the biggest one, it's like an average. So I think it's kind of cool to see those numbers to have an idea of the speed of the traffic. Cool, and so the last part of the pipeline described this miner script. And really I want to talk about this graph-oriented data mining technique. It's going to be a little abstract, but please bear with me. So as security analysts, security researchers, we have to deal with a lot of different internet entities that we see in our logs. Domains, URLs, IPs, ASNs, hashes, binary hashes for viruses that are helpful to do signatures for antiviruses, emails and regexes as well, a lot of different ways to approach this data. And a lot of the external APIs, a lot of external vendors have indicators as well, such as Investigate, this is us for OpenDNS, MaxMind, VirusTotal, Showdown, or even like we can grab the HTTP content as well to build our own indicators. And also like some custom models, and this is the case of NLP rank today. And really one way to aggregate all this information in order to take an accurate decision is to model it in a graph format. And really, this is probably the most beautiful data structure you can use in our case. So this is just a simple example, so you can have a precise idea of what I'm talking about. Let's say you have a regex, and that regex matches a couple of domains in your logs, and this domain is registered, through the whois data. That would be a certain email registrant email. Sorry. This domain can point to a couple of URLs. Those domains could be hosted on the same IP, which would belong to a certain ASN, and this ASN could be located in a certain country. This URL could be hosting some viruses, some malware, using certain hashes and signatures. So really, that's a way to aggregate all of these indicators, all of these entities, and to connect the dots to be able to have to step back and have a larger idea, to see the bigger picture, basically. So now that you see that, really what we're doing when we're doing data exploration, once we have aggregated all these indicators, really we're doing a breadth-first traversal. So if you're not familiar with it, it's a simple graph algorithm. Think of it as a Facebook. You start from your own profile and you visit all your friends, the friends of your friends, the friends of your friends of your friends, and you do that as many times as you want. So for us, we start from a domain, from a URL, whatever, and we explored all those indicators and we try to take accurate decisions based on the neighborhood of a certain node. And this is why having a graph representation is really important. However, with so many inputs and seeds to mine from, might be super long to actually operate that. This is why we have to opt for like a distributed breadth-first traversal. So really, this is what the miner is doing. It takes all those outputs from the Avalanche pipeline, mining all the external APIs, HTTP content, running some machine learning algorithms, and trying to take a decision all at once. And this is how we actually do classification. So really, you can think of it as, I love to call that lambda mining, because it's kind of a functional graph exploration process. This is how, again, we can apply some rules, some threshold, or like do some topology-based detection. So the wider problem is called subgraph isomorphism detection. It's actually an NP-complete problem. This is why we have to opt for those smaller kind of solutions. Cool. Now let's move on to the next part, and we're going to talk about NLP Rank, which is our amazing, phishing detection plugin using machine learning that Jeremiah has been working on for the last, 2 years, 1 year, yeah. Something like that. Yeah. Okay. And we have to do a quick transition. Thanks. All right. Thank you.
Cool. Can I take those out?
Yeah. Thank you. Sorry about that. All right. Can everyone hear me? Yeah, cool. So basically, this is the text track, so let's get into some text mining, right? So basically, using NLP to find phishing pages or fraud detection. So just to give you a little kind of example at the beginning. So this is a phishing domain. So basically, you could see from the whois records. This is a UI for our product, Investigate of OpenDNS. Basically, you can investigate different domains from DNS traffic that we see. You could see it's registered or created February 9th of 2016, updated February 9th, 2016. Okay, so and then we saw that spike just like around February 9th. So and you could see the top line is what basically I see every day to view our results. So this is the time it was detected, the timestamp. Here's the domain, and basically this is the score. You could think about it as a probability that is a phishing page, and this is the page that basically I trained it on. And I'll get into explaining it, but basically the probability that it's 99.9% a phish. Okay, and boom, you can see that's what the actual phishing page is from our traffic. So just to give you a little flavor at the beginning, just so keep you guys interested. So let's get into it. So basically the overview of the model is it's a fraud detection system using NLP and unsupervised machine learning techniques and traffic features to identify domain squatting and brand spoofing in DNS. Basically, this is a common technique by phishers and APT CNCs. So, and just a little pay homage to the kind of origin of our data that I trained it on is Fish Tank. If you guys know about it, it's pretty well known in the security community. Basically, it's a crowdsourced kind of based system where basically the community submits fishes, potential phishing pages. People vote on them. Basically, it takes a little time to like 20 votes to actually categorize it as a fish, and then also with the brand, and then we push that out to the whole community, and it's consumed by a lot of people. Google Safe browsing, for example. I mean, Brave, the new browser, just a lot of antivirus. So basically, it's a kind of a staple in the community. So yeah, and I'll get into that a little bit later too. So just a little psychology behind kind of phishing. So it's kind of falls under the category of human-computer interaction, right? So what kind of links do people typically click on? How do people get phished? What are people, and that has to do with people's interests, right? And so kind of the topics of interest would be, money, of course, news, security or software updates, and now the social networking, all these sites coming out. So just a little psychology behind the attack, because it really has to do with kind of like human and social engineering, right? So just for this presentation, we focused on big name brands. I just want to kind of like emphasize that, like the most phished brands. And you guys, I'm sure, have seen like PayPal phishes and received them, Apple phishes, asking for your Gmail creds, whatever, Wells Fargo. So yeah, just for this presentation, focus on that. So this is the kind of overview, kind of like a diagram I show for, basically I'll keep referring back to it as I kind of like step through the pipeline of the model. And so you guys will get a better picture. So basically for the input, it could take DNS or HTTP traffic, like a domain name or full URLs. So the first heuristic I have, and this is just a filter, is basically an ASN filter. And you could think of ASN, so I have a whitelist. We have a whitelist, as Thibault mentioned, for 0MQ, the Avalanche, basically through our pipeline. So that filters out a bunch of traffic. So we deal with so much traffic. The first step is to remove everything that we don't need to inspect, because text mining is computationally intensive, right? So then after the whitelisting, we have an ASN filter. And you could think of the ASN as your zip code on the internet, right? So if you were expecting some kind of like Gmail update or Java update, right? Most likely, if it was a domain name registered by Google, it would come from Google's ASN or Oracle's ASN, right? So you could think if anything coming out of that zip code that has like some kind of like Java update, you could automatically think it's some kind of like weird kind of like, anomalous, right? So that's the first step, just filter out as much as we can. So then the auth logs come in, and basically the Avalanche will enrich them too with a couple of other things like the ASN from the GeoIP lookup, and they will filter by that, right? So the second heuristic, right, getting into some text processing now, is we're defining a kind of like malicious language among internet fraud, right? And this kind of has to go with kind of the human computer interaction and psychology, right? You're advertising some kind of update, right? Some kind of bank update, to your bank account update, or software update, or some kind of verification login, right? I use the edit distance algorithm here, and kind of like some custom regexes, kind of applying automata theory, kind of defining different languages among the domains, and I'll get a little bit more into that. So what I did first was kind of just some basic data analysis. Out of the URLs and domains on FishTank and kind of in general, a corpus I built of APT CNCs, I extracted words that were in the dictionary, and I also stemmed them, because sometimes they might use the root of the word, right? So basically, mail, news, you could think software, server, update, right? Online, free login, secure, right? And so basically, that was the first step. And then basically also just extract the most likely, the top domain, or top brand names. So Apple, iCloud, Wells Fargo, Bank of America, B of A. So basically, one of the ideas came up with is looking at brand names plus what I call as an advertising action word. So basically, Java update, Wells Fargo secure verification -online.net, right? Something like that. Those are most likely, like what these phishing domains look like, right? iCloud service update, whatever. So, but the basic idea is you have a brand name and you're advertising kind of a, some kind of action to get the user to click on the link, right? Here's some examples. I mean, and so basically, also what I did. Here's an example of using automata, kind of like the kind of defining the language among regexes. That would, for the edit distance, sometimes it'll be a one-off, like PayPal with a 1 at the end instead of the L. But we can't set a large distance because otherwise we'll flag too many FPs and too much computation, right? So basically, what we do is build kind of like a language among these, so that allows like different variations of these letters. So with basically, we're allowing a higher distance, but only in certain cases, right? That's the kind of idea. Here's just some examples of phishing examples. And you could see from here the advertising action words, wellsfargo.com.billing.account.updatemyaccount.wellsfargo.com.onlineaccounts. So you guys see it, you get the idea, right? So these are kind of anomalous already, right? Wells Fargo online, this is update bankofamerica.update.login.info. So here's some examples of like APT CNCs, and in the security community, it's kind of like one of those kind of markety terms, but I just use it as a labeled data set. So it stands for Advanced Persistent Threat. It was a term created by the Air Force, but it's thrown around a lot at conferences like RSA and stuff like that. So, but basically, we're just using it as a labeled data set, and you could see these domains exhibit that kind of those kind of features too. And these are more targeted attacks, but you could think of these as kind of like target at big companies, right? Lockheed, Sony. So just a lot of So. Okay, so yeah, basically I explained this, kind of creating a malicious language. So that's just on the domain name. When we see it in the traffic, if it exhibits these features, flag it, right? And then I'll get into the content mining, right? And just an overview of the edit distance. So shortest path dynamic programming from algorithms class. Google, so this is 3 edits, right? So Goog with its zeros, 1, 3 edits. Dropbox with zeros. Bank of America with, change the the O's to zeros, E's to 3s, I to 1. So yeah, 3 edits. So just a basic overview. You guys already know. Okay, third heuristic is HTML content mining. So this is kind of where it gets interesting. So first, once the domain exhibits those features in the traffic, we do a GET request. We check for form fields on the page. We get counts. Convert to TF-IDF space, which is another text processing algorithm. We apply latent semantic indexing, basically a topic modeling. We grab the topics of the web page. So you could think of it as basically content mining web pages, right? And then we compare cosine similarity to basically a corpus, right? That's already converted to LSI space, and we just compare vectors in the corpus. So any input page comes in, exhibits those features, flag it, grab the content, convert it to LSI space. Then we have a corpus already converted to LSI space, compares through each of them, just iterates through, and finds the cosine similarity. And that was the score I showed you in the beginning, the 99.9%. That's the cosine similarity score. So you can think of it as a document similarity problem. These phishing pages, oftentimes they'll just copy the exact HTML from the original page, wellsfargo.com, the login, and basically use that, right? So that's basically one of their primary method. So here, kind of going on against, like with the AI idea, we're recreating a security analyst, basically, to do our phishing detection for us. You could think of when an analyst or researcher investigates a website that's in question, you look at it in a Tor browser, then you get a summary of the page, and basically you decide what the page is about. So we're creating a summary of the page or getting topics of the page, right? I just like this quote, unsupervised learning is the future. It's all about the features, and that's what we're using, LSI, unsupervised algorithm. A lot of, these days, so much data is being generated, we can't even process it. Even through supervised algorithms, humans have to come up with those features. So we need a way for the machine to generate features, right? That's my only point. So yeah, I'll go through. I use GenSim library. Highly recommend that, text mining. Check it out. And it's being developed on by Google Summer of Code. They hired a couple of interns, but it's awesome. So knowledge discovery algorithms, and it's super awesome in Python. Yeah. So yeah, building the corpus, basically pages from all different brands, focus on big brand names. And the reason I had to build a corpus is because there's 90s PayPal, 2000 PayPal, all these kind of like older phishing sites. So, and that's not updated with the original legitimate site right now, right? So TF-IDF, basically this is the kind of overall just algorithm. So basically, it's not only if the term is relevant, basically if it's high frequency, but also if the term is rare. So we want to kind of merge that together, right, to find the important words. And you could think, here I just gave an example on TF-IDF on Shakespeare's Macbeth. So the top 10 is, Macduff, Macduff, fear. So topics, right, fear, murder, that's what the play is about, right? So just to, for example, witches. LSI, kind of like nasty linear algebra, long story short, a lot of kind of matrix decomposition. So yeah, we have basically decompose. So we have X is the count matrix, M is rows, and N is the number of columns, and this could be also the TF-IDF matrix. We pick value K, which is the magic number, the black magic number, right? And then we decompose X into 3 matrices, M by K matrix, where M is terms, K is the number of concepts, and S, which is the K by K matrix, kind of like emphasizing the variation, right, among the topics, and V transpose, which is what we're interested in at the end, where K is the concepts and N is the number of documents, right? So that's what we'll be comparing, right, the vectors. So yeah, and then get the cosine similarity, which is basically like the normalized dot product. Sorry, going a little fast, I'm a little short on time, but I just want to get to the results. So yeah, then here we process the documents and then push them to our block list. So we are blocking real time now. So, and then we get kind of analyze the rest of the results, rebuild, retrain, right? All right, let's get to the results. So this is kind of what it looks like. So it gives back a top, however many scores we want, but we're taking the top one and we're blocking based on that kind of whatever is the closest to. So if you have a input query Wells Fargo, that's the input domain we caught, and then it compares, and you can see here it got closest to the actual Wells Fargo, the legitimate site. So I have legitimate sites and phishing sites in my corpus, right? Here's some k-fold cross-validation for proof, and this is trained on the fish tank data. But yeah, any questions, talk to me later. So here's some dedicated examples. So when I say dedicated, this is dedicated domains set up for phishing. So PayPal-update-account.info versus some site that already got hacked, like WordPress, something Makinas, .com.br, and then they have PayPal-account.update. So basically, it's a site set up directly for phishing, not a hacked site serving phishing pages too. So this is dedicated example. So the setup. So here's iCloudServer.ru, detected 98% cosine similarity, and yeah, basically we detected it kind of here 5.8. So you could see right here on the May 8th, we detected it. It was created a while ago, but still we're detecting it right away, and we block it right away, right? iCloudServer.ru, boom. Russia, Moscow. Web apps, PayPal.com, detected February 11th, created February 10th. We saw the spike, February 11th, blocked real time. Boom. Google Drive.com, 95%, we see it basically. And what we're doing also, we pivot on these domains. So look at this email address, smilosevic.yandex.ru. Kind of looks suspicious. That's the page, boom. And now there's a bunch of phishing pages associated with that email address. This is what we do. What happens when we pivot on the IPs too. So here's securityapple.inc, detected 94%, close to iCloud. Boom, it's in iCloud. And look at that, trusted Gmail, so same email address, and have much more phishing on there, right? Apple ID privacy, which is right here, first one. Boom, it's all fish. Gmail remind.tk, 96%, right? Looks kind of, funky. So basically, and we pivoted on the IP, and it's all phishing on that IP. So we block that IP. Everything that comes up there automatically blocked. So this is dedicated kind of phishing examples. Same thing, that Yahoo reply was one of the domains down here. Boom. Google Secured Center. Yeah, so then pivoting on that email address. Yep. And now these sites are just being secured Google, so they haven't even came up with the site yet. They just spin it up getting ready. So it's kind of predictive. So I don't like to throw that out too, but it's one of those kind of terms, the buzzword terms. But basically Twitter, I just emphasize here is that we're detecting different brands. Wells Fargo Bank.mygeno.ru. Compromised sample, so this is a domain. So here's the phishing page. And here's, if you look at ruralmaquinas.com.br, boom, that's the original page, the landing page, right? So these are hacked pages, google.com, Stephanie LaSalle, boom. You get the point. And here's just some more compromised pages. I didn't put the landing page, but that's what we're detecting. It's kind of like as example. I just wanted to show we're detecting a lot of brands. Obviously, we have false positives, but basically what model doesn't. But here, what we're actually finding is that Mark Monitor, which is a service that does brand name protection, which redirects back to the legitimate page, this is a good kind of like test set within live data. So we're on the right track, and we were able to filter those out based on like the WHOIS records. So now we're not really blocking those, even though kind of Mark Monitor already does that service. So it's a whole company based on this kind of idea. So yeah, you could see Mark Monitor right here. Here's another example of a page that we hit on, but pay-for-install.ru, which basically redirected from that play.googles.re, which is, no one will miss this page if we block it anyway, and it looks kind of suspect anyway, because there's some phishing or like typo squatting on that email address. Here's some more results, a lot of high 99, so high 90%. So stacking models, so we're combining this model with our spike detection model, so we could see kind of large-scale phishing campaigns happen in real time. You could see this is an iCloud Safari page, so iCloud page, and it has over 2,000. So basically, analyzed spike requests by one of the other models. A couple of our researchers developed. So stacking models. That's the only point of that. Other clues, basically some other crap in the page mirrored from Google.com. So yeah, here's some like just one of the bad kind of like Carbon Act domains. So basically Russian APT. They kind of like exhibit those update-java.net. That was a banking Trojan. Yeah, so I won't go into this, but just because for sake of time. But basically, there's just a lot of crap out there. Yeah, and so for future work, reduce validation time on fish tanks and push out to the community. So it could be used to detect fishes. So basically, anything that people push to fish tank does not have to be verified anymore. It could just be run through this algorithm and push out. Integrating with the Cisco proxy and the email corpus, building, testing, and tuning the algorithm, and detecting target attacks, and we're moving to Apache Spark in that direction. So yeah.
Cool. Thanks, Jeremiah. Yeah, so very quick conclusion, because I think we're going a little bit over time, but in the security industry, like it's a lot of people usually claim that they do machine learning, but actually when you start scratching the surface, it's not really there. I really would like to give kudos and shout out to Jeremiah, because he's been working hard on that. And it's actually something that's running live, blocking live traffic. Every day we see like new stuff that is happening on the internet. And really, like if you look at all these examples, sometimes the domain has been like set up maybe a couple weeks ago, but we see the first request, 10 minutes later, boom, it's blocked. And that's, for me, that's really impressive. If you're interested in learning a little bit more about what we do, we have a blog. Go to labs.opendns.com and you can see our kind of daily task, and we blog about everything we do. Special thanks to obviously the analyst team who helped us review a lot of those domains, marketing team for those slides, obviously, design team, Tasha, and also obviously the Data by the Bay. We wouldn't be here today without them. We don't have much time, but let's do maybe a Q&A session,
yeah.
Short one.
Yeah.
I mean, if we don't have time, you guys can always come see us. We'll be happy to answer your question and hear your feedback.
How up to date do you have to keep your models or your corpus?
That's a good question. That's a really good question. Yeah. Okay. So basically, yeah. I mean, I go through and I update it like basically pretty often, like weekly. But the thing is, we just have to keep on top of certain trends, and sometimes they might modify the actual legitimate page, like whatever the iCloud landing page or Wells Fargo. So we like basically periodically add that to the corpus too. But I'd say an ideal time is monthly. But we see like ideally like weekly or bi-weekly, and I think one of the things that I'm working on really is kind of analyzing a way that we could just retrain from the fish tank data automatically, and it updates the corpus, every so often. I think, maybe daily or kind of like, a couple times a week would be ideal, just to keep on top.
How do we handle the cross-boundary? Is it possible for you guys to block them?
Yeah, so if we're not seeing that many false positives in the top traffic, actually, but the thing is, basically, if it's a page, we filter out the mark monitor stuff, but if it's a false positive, we have a popularity score to kind of check against too. But basically, if no one's really going to miss it and no one complains, then we don't really care. But I mean, for the top stuff that's automatically blocking, there's almost none. Yeah, it's pretty similar.
Yeah, one in less,
Yeah.
2-3 weeks.
So people will call you guys and say, we need some.
Yeah, basically, yeah, they'll say that. But yeah, but usually they're kind of not like, they're not necessarily phishing, but they're kind of suspect pages anyway. Yeah. Yeah. Yeah, and a lot of coming from like some weird provider in Russia, and kind of you saw the false positives that they have other but basically there's other stuff that's on that IP or like domain or like email address that's already bad too. So it's kind of like suspect anyway. Yeah.
Gotcha. Thanks.
Anybody else?
Maybe it might be that one question is how do you decide the sort of cost function of how many false positives you like versus how many false negatives, how do you sort of tune it?
Yeah. So what we do is we set a very two different thresholds. We have basically one thing that flags and automatically blocks stuff that we're like super confident about, like very little false positives, like none. And then we have like this kind of other range where we have like review that sends to like our security analysts that they review. And sometimes some of them are a little bit more false positive prone, but some of them are still phishing. So we're trying to work that too while we get some more features and stuff. But basically, for the stuff that's automatically blocked, there's almost none.
I was wondering how much bandwidth for the bug you get from looking at the domain name URL versus the content?
I mean, if we could flag just based on the domain name, of course that would be nice, right? But the thing is, there's a lot of stuff like the DNS is a jungle, and there's all these type of stuff that looks bad that might not be, or kind of having people register kind of weird stuff anyway. The content mining is basically to create its own analyst within itself that we don't. So we want to be sure, because if we block something that's not really, we don't have too much like confirmation about, especially kind of like new stuff that comes from Google, like that might be on some kind of like weird ASN that doesn't have to do necessarily with the zip code. We want to be sure we're not doing that, And basically, the thing is that we don't want is customer complaints. So we want to have as in-depth models as possible, and it's still faster than humans. So, way faster. So, I mean, literally from all we need, like Thibault said, all we need to do is see one query, flags on that, and do a lookup, and then it's blocked from the convert it to vector space, and then it's compare against the corpus, and it's automatically blocked. So within that time period, I mean, humans can't do that anyway, so we're still faster. So yeah, it's not really, just takes more resources, more machine kind of power, but it's a pretty cool problem, I think, and kind of a lot of companies do it kind of this idea of categorizing the internet, content mining, because this can also be used for, we've also used this algorithm to discover kind of stuff on like mining the dark web, so for like drug sites, child pornography, kind of all different. You could use TF-IDF and topic modeling to discover those pages too, which is kind of cool. So, and this is kind of how they do website content classification. This is a search engine algorithm. So, yeah, cool.
Thank you very much.
Thank you.